Michael, it's okay, buddy. If you tried, that's, you know.
I'm trying to use my time management skills.
So let me explain what's going on here. All right. So wanted to give you guys some time to work on that by yourself, right? You've tried, and this quiz kind of gives you an indication of like typical test questions, right? So as you're studying for test 2, you can look at like this quiz and the last one, right? And the solution, which I will post, of course, in Canvas. And so these should be an aid to you as you prepare for the next test. On the other hand, I wanted to reduce your stress, so I'm not collecting them and grading them. We're just, if you're here and you took it, you get full credit. So let's look at the solution together.
But I don't want to look at the solution. I don't want to.
Yeah, well, I'm sorry about that.
Or I'll just look down.
Excuse me.
Oh yeah. You can also just.
All right. I will eventually open the solution. Here we go. So for problem 1 here, to solve that, you want to isolate a radical. I chose to isolate the 2 times the square root, and then I squared it. I could have divided by 2, but I chose not to because that would have brought fractions into the fray. We don't like fractions. So squared it. I collected terms. I isolated the radical again. I squared it a second time, and out pops x equals to 0 and x equals to 16. Yes, Michael. Yes, Michael.
Can I leave 0 as one answer?
0 is one of the answers. That's true. There are 2, though. It could either be 0 or 16. Both work for problem number 1.
Oh.
Yep. Now for problem 2.
Let me take a photo.
Well, this is posted in Canvas, Michael, so you can look at it there. So you don't even need to take a photo if you don't want to. This PDF is posted in Canvas for everybody. Okay?
I'm sorry if I didn't finish.
You're fine, Michael. So the cursor is in the way this time. So we're up against the 3/4 power here. So what do? We raise it to its natural enemy, the 4/3 power. The 3/4 and the 4/3, they cancel and just give you 1. So 2x minus 1 to the 1 power, which is just 2x minus 1, equals 8 to the 4/3, but 8 to the 4/3 is actually 16. So we get 2x equals to 17, which gives us x is 17/2. So that's how that went.
I like to try to figure this out on my own.
Well, you can do that, Michael. So now this one here, listen, like the way I did the steps here, you might have done it a different way. But after I collect everything together, I ended up with x to the minus 1/2 and y to the minus 3/2. So I found my a, quote unquote, is minus 1/2 and my b is minus 3/2. And this one, I didn't even have like some of these problems I've been making it have a constant in the front, c, right? But this one I didn't bother with that. Now here, this is a case-wise defined function, right? So we got to figure out which case we're in. F of 2, well, 2 is less than or equal to 3, so I use the first case. So 3 times 2 squared plus 7, also known as 3 times 4, which is 12. 12 plus 7, 19. That's how that goes. On the other hand, 4 is greater than 3, so f of 4, I have to follow instruction number 2. I get 2 minus 4 cubed, which is 2 minus 64, which gives me minus 62 for that one. Then, last but not least, the graph problem here. So how many of you got f of minus 2? See, f of minus 2, where is minus 2? Uh-oh. What? Hey. That's not cool. Oh man, I must have been really asleep when I wrote this solution. Do you guys agree with that?
No.
I surely don't.
Oh, well, I was trying my best.
That's good. That's good. So why is my answer here wrong?
Because it's actually negative.
Where is minus 2 in this picture? It's right there, right? Oh, I'm an idiot. I thought that there was just the circle here. I didn't notice the dot. I was awake when I wrote the solution. Hooray! Okay, so
To have a perfect day, and I ruined it by getting distracted.
it's all in your mind, Michael. There's nothing wrong. Just relax. Let's see here. So f of 2 minus 2, that dot right there is 4. That's why I wrote the 4, because of the dot. Yeah.
If you have two, which one would you choose?
If you have 2, it's not a function. That's not allowed. That would be a violation of the vertical line test, which I should talk about. The domain, everything is covered here, even minus 2 because of the dot. Although I will admit, this particular problem, if the printer doesn't do a good job on a given day, I'd have to like count many answers as correct, because I can hardly see the dot, but oh, whatever. But 4 is missing here, right? So 4 is outside the domain, and it begins apparently at minus 6 and it ends at 8, as best as I can read the PDF here. So that's why my domain is minus 6 to 8 with 4 excluded. And the range, the y values, well, the lowest one is minus 4, but it doesn't get there. And the highest it goes
Did I
to...
figure out the rest of the quiz in your office?
You can if you want. So then 6 up here is the highest value it gets to.
That makes sense.
So that's the range. All right, so we should move on though. This is a review of things we've done. So other things I need to talk about today.
Well, I totally blew the quiz.
And you still get 10 points for it.
The full credit.
Yeah, everyone who takes it gets full credit. Michael.
That this isn't right.
This isn't right. Michael, don't. Michael, be quiet.
But I just want to have a perfect day.
It is a perfect day because we get full credit for quiz we don't get.
But I wanted to get.
But you do not have to. That's what we
All right. 90.
You did your best.
Oh, it is not a perfect day. You're right, Michael. Look at this. Ah, the hideous Carolina blue. It has appeared. Ah. Why does that marker last so long? It should have died. Why must the evil not die? It's Carolina blue. It's Carolina blue. Carolina. All right. So we've talked about functions, but I mentioned the words vertical line test, but I haven't talked about vertical line test. We should talk about that. What is the vertical line test?
Oh, shoot!
So,
That was really late to the point.
yeah.
Oh, me?
What's
Yeah, so vertical line test, it's so an x can have 2 y's.
an x can't have 2 y's. That's it exactly. Yeah. Perfect. So if we have some kind of, shape like this, for example, suppose that's your graph. All right. Is that the graph of a function? Listen, a graph could be any subset of the plane. So like a graph is a very general idea, but the graph of a function has to pass the vertical line test. This fails the vertical line test because, like you just said, there are 2 y's for 1 x. So if when you pass a vertical line through the alleged graph of a function, if you hit 2 different points, it's not a graph of a function. See, because y must be equal to f of x. Okay? So if this point was like, minus 2, 1, and this point up here was minus 2, 4, then I wouldn't know is f of minus 2 equals to 1? Or is f of minus 2 equals to 4? See, I couldn't, which one would it be? Like you guys were just asking me, if I have two dots at the same x, what do I do? Well, the answer is you send the question back because your instructor gave you something that's not a function. That's outside the bounds. You're not allowed. It's not allowed. It's forbidden. So this is the vertical line test. Now, sometimes you don't want to graph something, right? Sometimes you can basically do the vertical line test at an algebraic level as follows. So example 1, does x minus 3 squared plus y plus 2 squared equals to 100 define y as function of x. All right. There's two ways to solve this problem. All right, so let me show you the 2 ways to solve the problem. The first way is by algebra. So number 1, here's the algebraic solution. So the algebraic solution is simply this: solve for y. All right, we try to solve for y. And if when you solve for y, there's more than one solution, then guess what? It's not a function. All right? So can you guys tell me how to solve that for y? I'll start us out. Y plus 2 squared is 100 minus x minus 3 squared, right? So I've isolated the term with y, and then what do? I use, yeah, Michael?
Square root.
Square root property is correct, yeah. So we take the square root of the equation. Remember, we have to allow for plus minus, yeah? So this gives me y plus 2 is plus or minus the square root of 100 minus x minus 3 squared, right? So finally, we've got y is minus 2 plus or minus the square root of 100 minus x minus 3 squared. And so there it is. We solve for y. So this says not a function, since plus minus gives 2 solutions, not just one. Why is this happening? Can anybody tell me what's the graphical solution to this problem? Can you guys tell me? The graphical solution, as you might have guessed, is graphical. Yes, Michael?
The radius is -2, 0.
The radius, you got the right idea. Can anybody help Michael? Where's this? This is a circle, right? Where's its center? What is this up here? This is a circle, isn't it?
Yes.
And it is this centered where? 3 minus 2. And what's its radius? Can you get anybody tell me what the radius of the circle is?
So
I heard a 10.
super.
Mm-hmm. Square root of 100 is 10. That's right. So the radius is 10. That means that this goes plus or minus 10 from there. So it goes like up to 8. It goes down to minus 12. It goes over to 13. It goes back to minus 7. It's a circle.
Oh, wait.
So the top of the circle, right, is exactly what we found algebraically. You see it? The top of the circle is the plus. That's y equals square root of 100 minus x minus 3 squared. And the bottom of the circle is the minus solution, right? And you can see clearly that we fail the what? Oh, I've lost my 2 there, didn't I? That's y equals minus 2. God, come on. Goodness gracious. Y equals minus 2 plus that. Y equals minus 2 minus that. So, you know, unless I gave you instructions otherwise, you could just be like the graphical solution and say, well, it's a circle. And so there you go. Fails vertical line test, right? Sorry, let me get my junk out of the way.
Hold on. Let me take a picture.
Okay, Michael. Yes. Go ahead.
So, on like one of these, let's say that we're doing the graphical solution. So if there was another problem that would be a circle, can we just say that it won't be a function when it becomes obvious that it's a circle? Because no matter what the circle
Well, if the formula is a circle, you can say this is a circle. You can draw a circle and draw a line through it. Fails vertical line test. That would be a solution. Yeah. However, some of the problems in your homework have more specific instructions. They say solve for y and explain whether or not it's a function, right? So then you need to do the algebra. So let me show you one where it is a function. Example 2. If we had, I don't know, let's say x plus x squared y cubed equals to 7. The question is, does that equation define y as a function of x? How can we decide? What do we got to do? And by the way, guys, I will get back to the graphing with transformations. I'm sorry, I'm kind of jumping topics here. We will get back to the graphing with transformations in a second. I was just feeling guilty for not talking about vertical line tests. I'm coming back to it. Man, whatever marker was here before, it's just really, really hard to erase. Yowzers.
What section is this on?
It's chapter 2.
What number?
Chapter 2.
Chapter 2? That doesn't make any sense.
I do not remember which section precisely this is in, Michael. But probably like 2.2 if I had to guess, maybe.
Oh, circles.
Well, the circles is from before, but the question about what's a function, that is
Functions.
should be covered in
2.3.
2.3 possibly. Yeah. Okay, so this one here, if we try to solve for y, what do we get? So let's see here. Isolate the y cubed. I got what? I've got x squared y cubed is 7 minus x. So then divide by x squared. I've got y cubed is 7 minus x divided by x squared, right? Now, when we take a square root, we have to do plus or minus. What about a cube root? It doesn't, right? The cube root of y cubed is just equal to y again. In contrast, the square root of y squared is actually equal to the absolute value of y. And that's why we have to put a plus or minus y in that case. That's the difference. If you have an even root, plus or minus. If you have an odd root, No plus or minus. So odd roots tend to give you functions.
Odd root, even root, plus or minus.
Right, so here we have y is equal to the cube root of 7 minus x over x squared. There you go. This is in fact a function of x, just a single value, all right? Now, don't ask me to graph it. I don't want to graph it. Do you want to graph it? No, but we can do the algebra, right? Okay, so let us go back to transformations of graphs again. We need to talk some more about that. And I mentioned to you guys there were 2 more to talk about, right? So maybe 4 more, I suppose. Here they are. So yeah, y equals to minus f of x is y equals to f of x flipped over x-axis. If we look at y equals to f of minus x, that's y equals f of x flipped over y-axis. And if you don't like the word flipped, you could say reflected. That's kind of the more usual mathematical term, reflected. So reflected across the y-axis, reflected across the x-axis. And then the other 2 things we sometimes think about are this: y equals to a constant times f of x is y equals f of x stretched vertically. And finally, y equals to f of cx is y equals f of x compressed horizontally. So those 4 transformations, together with the shifts that we talked about last time, that's pretty much it. And honestly, folks, I don't think as much about the stretching and the compressing as I do about the reflections and the shifts. Let me give you an example. So let's see if we can use transformations by graphing to graph the following. We want to think about y is equal to 3 minus the square root of x plus 2. Let's see if we can obtain the graph of that by transformations, all right? So how does that work? So what we're going to do is we're going to start with y equals the square root of x, right? That's our basic graph. We know how that goes. And then I can take that and do what? I can change that to the square root of x plus 2. How do I do that? Geometrically, what is that? Shift what?
Shift to the left.
Yep, shift left 2. Left 2. And then I can trade that for minus the square root of x plus 2. What's that? What is that? That's a new one. That is flip over the x-axis. That's a reflection over the x-axis. And then what else? We still one more move, right? One more move. Yep, we go what?
Up.
Up 3, yeah. So we have y equals to 3 minus the square root of x plus 2. All right, so that's the game plan. Now let's actually carry it out. So here's my initial square root graph, right? Then I move it left 2. Wait, left. So left 2. Like that, yeah. And then I flip it over the x-axis. So this was, let me give these numbers. Let me call this one number number 2, this is number 3, and this guy's number 4, okay? So, and this was number 1. So here's 1, here's 2. I get tired of drawing so many axes. So if you don't mind, I'm going to do 2 and 3 on the same picture. 3 is flipping down like this. So there's your 3. And then step 4, finishing blow. Let's see here. We take that, and where's this point right here? That point's kind of important. Where is that? That's minus 2, 0, right? So that is the anchor point, if you will, for the square root. And so that is going to shift up 3. So it goes from minus 2, 0 to minus 2, 3, which would be like here-ish. And the graph is, let's see here. Let me think about that for a second. When I plug in 0, I get like, all right, well, it is what it is. Up to the limits of my artistry, there you go. Now, last time we did this, we were talking about horizontal and vertical shifts, right? In that situation, those are a little bit easy. I told you guys those were easier, right? The reason that they're easier is it doesn't matter which order you do those in. Like if it's just shifts, you can shift horizontally first and then vertically second, or you could shift vertically first and horizontally second. Wouldn't make a difference. But with these, if I reflect first and shift second, it's different. The order matters. I have to put that minus just hitting the square root, right? I can't reflect at the start. Well, I mean, I guess I could. I suppose I could have reflected at the start and then I could have shifted it. But the order matters. If I did these steps in a different order, I'd get a different graph, okay? So, something to be aware of. Example 4. How about if we have y equals to, I don't know, 2 plus the square root of minus x. All right, so here's what we're going to do. We'll start with our y equals square root of x, right? And then my next move will be to flip it over. But this time we're going to flip over the y-axis, right? So here's what y equals to the square root of minus x looks like. All right? And then what do I do? Anybody?
Going to go up 2.
Yeah, then I go up 2. So finishing move here. There you go. That's y equals to 2 plus the square root of minus x. And that y-intercept right there is 0, 2. Now, transformation by graphs is a very useful method of graphing once you get used to it, right? But you should always remember you can check things, right? At the end of it, you should be able to plug in some points and make sure it makes sense, right? Like, let's try this one, for example. Just to double check my work, here we have f of x is 2 plus the square root of minus x, right? What happens when I plug in, for example, f of minus 4? What do I get? What is?
Try to catch up.
You're fine. What is f of minus 4? Well, we have 2 plus the square root of minus a minus 4. What's minus a minus 4? Well, it's just 4. What's the square root of 4? 2. So we have 2 plus 2, which is usually agreed to be 4, right? So I think that tracks with my picture, right? If you look at plugging in minus 4, you get 4. So about right here, this point is minus 4, 4. So, what I'm trying to tell you guys is, if I give you a transformation by graphing problem, you want to check yourself, you can always just plug in a point and make sure it makes sense, right? In fact, in terms of methods to graph, this is something we can always use, is just plugging a point in to get a point on the graph, right? That's something we can always fall back on. Okay, so I should move on here. Let me see where I am here. So the one thing I haven't talked much about yet is symmetries. So what are symmetries of graphs? Yes, Michael?
The symmetries are that it reflects identical both in and out.
It reflects identical both in and out. I guess that's...
It is the same.
It is yeah, symmetry means same, some kind of sameness. That's good. So for graphs, there are three main kinds of symmetry that we generically look for in graphs. And the words we use for this are even function, odd function, and also symmetric about the origin. So let me just give you a careful definition, yeah? So definition, if f of minus x is equal to f of x, if f of minus x is equal to minus f of x. So this then, f is even function. And on the other hand, if it gives you minus, then f is an odd function. Sorry, I seem to have missed a word there, but you'll forgive me. Don't tell your English instructor. I think in numbers. Let's see here. That's an even function, that's an odd function. Symmetry about the origin. I'd rather just state more graphically. Symmetry about the origin, or symmetry with respect to origin, means if you have a comma b in the graph, then you also have minus a minus b in the graph. Okay, so goodness gracious. Now I guess I should probably not leave you here. Even functions, so that means it's symmetric about the y-axis, and odd functions are symmetric about the origin, actually. So example of that, example 5. If we have y equals f of x equals, let's say x squared, I'll keep it really simple. And example 6, we could say y equals f of x equals x cubed. Those are pretty simple. So x squared, what's it look like? Looks like this, right? Y equals x cubed looks like that. So this is a quintessential example of an even function. It's symmetric about the y-axis, see that? Whereas this is a quintessential odd function. It's symmetric about the origin. See, if this is a point down here, minus 1, minus 1, it gets paired with the point up here, 1, 1. So what does this all mean? This means one good test question to give you is to tell you, hey, here's half of a graph. Here's half of a graph, and I tell you it's an even function. If I tell you it's an even function and you've got half the graph, what can you do? You can create the rest, right? Right? Like, let me, if I'm not over time already. I'm not, woohoo! Example 7. So let's go with even function. Given f of x is even function, complete the graph. Complete its graph. So let us suppose that we're given this. Whee! All right. So I told you that's what's given, this annoying wiggle waggle curve. Then what does the rest of the graph look like? So I just need to mirror the same shape on the other side, all right? So it would have to look like that. Do we have time for something stupid at the end of class?
We have 1 minute.
You have 1 minute?
I'm sorry if I ever didn't finish the quiz in time.
You don't have to finish the quiz in time. That's the point. That is the point.
Oh, just take a deep breath and calm down.
Now that is very good advice. Have I ever proved to you guys that I'm Batman?
Is this going to be a reflection joke?
Let me pack it up.
So do you guys know about the Wu-Tang name generator?
No.
For example, Donald Glover is sometimes known as Childish Gambino. Sorry, it's very tiny. All right, so that's me. All right, so then let's search Batman.
Are you thunderous?
You got that? There's Batman. So I gotta make sure this is on screen here. There we go. So there you. So that's Batman. And all right, so let's try this out here. Check this out. Come on. Come back to me.
Wow.
As you can see, I am Batman up to a Wu-Tang equivalence. So anyway, yes. There you go. That's right. No, excuse me. Let me turn off this camera.